So power counting for general multi-loop integral or Feynman diagram. So let me remind you about the notation. L stands for the number of loops. We still want to work in n dimensions. We will see later why, but for now it doesn't matter. Okay, so instead of 4 dimensions, I am working in n dimensions. So for now you can imagine that the universe you live in has more than 4 dimensions, which is of course not true, but we can imagine. And n is the number of propagators, okay, which is same as the number of Feynman parameters. Okay, and after doing Wick rotation of both the physical and loop momenta, sorry, not physical, let's call it external. You can call it physical also. And loop momenta. Momenta. We had found the following. Okay, I'll drop these factors of I, pi, and n minus 1 factorial or gamma n, what we had earlier, and just concentrate on the important part. Okay, should I go to next page? Or maybe not. So we had, let me keep gamma n, which is n minus 1 factorial. So we had this following. We had dx1 up to dxn. Then you have a delta function which constrains all these Feynman parameters such that the sum is 1. Okay. Then after doing Wick rotation, our loop integral momenta, are like this. So L1 for loop number 1, this n, and you remember what this is, right? This is L0 when you take the 0th component of L1 and you do Wick rotation, that is what you are calling Ln. And then these are the remaining spatial components, which is n minus 1 dimensional. This is not a good notation. And the limits are from minus infinity to plus infinity. We have L loop momenta, so Ln dn minus 1 L. Okay. Then it stopped working. Then here is the denominator. And the denominator is this, minus x1 k1 square. I will tell you what I am doing. First let me write down x2 k2 square xn kn square minus m square. Okay, and I don't put any I epsilon because I'm already in the Euclidean space. You don't need I epsilons there. Okay, because there is a definite sign here. Okay, and what is x1, x2, so forth? Sorry, k1, k2. So k, q runs from 1 to that's not kn. What is? That's the number of propagators, and the number of propagators I'm saying capital N. So this should be capital N. Right? You have, for each propagator you have one x. So we should have x1 up to x capital N. Okay, let's say q is that index which labels this 1, 2, 3. So kq square is this. kq1 square. That's the first spatial component of k. kq2 square, or maybe I'll put this, otherwise it's confusing. kq we are working in n dimensions, n minus 1 square, and then the zeroth component after Wick rotation we were writing it as kqn. Right, that was a notation. That was for the loop momentum, and I'm using the same notation for q because k and l are related. So this is in Euclidean space. You see all the signs are plus. There is no minus sign entering anywhere. And kq is the following. The vector kq is but that's the vector kq. Okay, I'll just remove this arrow. Is alpha I q L I summation from I equal to 1 to I runs from 1 to what? It should run from 1 to the number of loop momenta, right? So that's what you are adding. So 1 to L plus summation over j beta j q beta qj, and then you have pj. Okay, and this is what is pj. J runs from 1 to the number of external momenta, external lines, E. So that's the definition. Okay, all I have done is just define. Let's go back here. Here. So you see here, the indices on x is suppressed, but this is giving you a factor of minus 1. So that comes out here, minus sign sits here. So you have minus of, and this minus also. Let's pull out both minus signs and just keep them aside for a moment. Then you have only plus signs relative to them. So you have x times this square minus x times this square. Okay, and this momentum, this entire thing, alpha li plus beta j pj, the sum of all these momenta I am calling k. Okay, so this becomes x times k square. This plus this becomes x times k square, and there is an overall minus sign, and that is what I have written here. Okay, so x times k square, or for x1 we have k1 square, x2 k2 square. And what is x1 and x2? These are just the, sorry, what are k1 and k2? These are just the momenta that are flowing in these propagators. So propagator number 1 has this momentum flowing in it. Okay, I hope you remember. See, whatever momentum flows, let me show you one of the diagrams, it will be easier to okay. Okay, let's see if I can find. Yeah, here for example, if you look at the propagators, okay, this will have L1 plus P1 whole square. So it is both linear in the loop momentum and the external momentum. The K, the corresponding K here, this is what I'm calling K1 or K2 or whatever. These are the Ks. Okay, so this is both linear in loop and the external momenta. If you go to any of these, you will have loop momenta summing up, adding up linearly, and also the external momenta will be adding up linearly. Signs may be plus or minus, but they will be all linear. Okay, and this is exactly what I have written in the general case. And this will be true for whatever diagram you draw. Okay, this is the sum of all L's with either coefficient plus 1, minus 1 or 0. So L1 plus L2 minus L3 minus L4, whatever. And similarly here, Pj's with all of the Pj's with some of the betas could be 0, some of the betas could be 1 or minus 1. Okay, so that's a plus, not a minus. Okay, so now we have this integral. We are almost there, and we can, just to remind you what we are trying to do. We are trying to achieve equivalent of this. Okay, so that I can do the power counting. Okay. Okay, good then. Now, because each of the K's is linear in L, the loop momenta, okay, and because we have a square, it becomes quadratic in Li's. Okay, so this this thing here in the curly brackets is quadratic in Li's. Okay, so I will just write down the most general form a quadratic function can take. So denominator is quadratic function of Li power capital N. And we are looking at this. So as I said, the degree of this thing is 2. Sorry, it's a quadratic. I will write down what it looks like then. So it will have a degree 2 term. And what will be the degree 2 term? It will be Li, Lj, right? It will be multiplying L1, L2, L1 square, L2 square, L1, L3, L4, L3 like this. And there will be some coefficients. Okay. There is Einstein summation convention which I am using. So it is, for example, A1, 3, L1, L3. This is one of the terms, plus A11, L1 square, and so forth. Then let's look at the degree 2 term. degree 1 term, it will have the form Li some constants Bi. So this is B1 L1 plus B2 L2 and so forth. Okay, and these Bi's are functions of stopped writing. I'm unable to write now. So all, let's call it J here, J. All the external momenta and all the Feynman parameters. Right, so B's will depend on that. You can see from here. Here, KQ has B, okay, and there are also x's multiplying here. So when you are looking at the sum of these k squares multiplying these x's, the linear terms will also have these p's entering them in them and multiplying them, and also the x's, and that is why I'm writing b is a function of x and p. If you are not fully confident, then you can write down a diagram with 3 propagators, okay, and a few propagators and 2 loops, and draw explicitly, and then you will see. Or just do this from here, you will see. Okay, and then degree 0 term, which is the constant term, I'll call it C. Okay, this will also be a function of these m square and external momenta. Okay, so there is nothing else, right? We have exhausted all the possibilities. So a quadratic function can only be a function of, will have a degree 2 term, degree 1 term, degree 0 term, there is nothing else. So the denominator is of the following form. Okay, now you see Aij is a real symmetric matrix. Okay, it is multiplying Li Lj, which is symmetric, so Aij is also symmetric. Okay, it's a real symmetric matrix which can be diagonalized. Okay, and furthermore, none of the eigenvalues will be 0. Okay, so it's a positive definite matrix, and because you have L, loop momentum is L, it's not going to be something which involves lower number of loop momenta after diagonalization. So this is a positive definite matrix, and all the eigenvalues will be non-zero. Okay, and then after diagonalization I can write it as Ai prime Li prime square Bi prime Li prime plus constant. Okay, when I look at this thing. So basically I'm doing an orthogonal transformation. So Li's go to Li primes, and these coefficients will change, of course. So this is the linear term. This term will, because we are trying to diagonalize this one by an orthogonal transformation, this is the diagonal form, and these are the coefficients multiplying each of the Li's, and then this is a constant term. Okay, now you can do another thing. You can see, going from Li to Li prime, the measure will not pick up any Jacobian because this is orthogonal. Okay, and determinant of these matrices will be 1, the transformation matrices. But then you can do one more step. You can absorb these AIs into these Li's. So you define a new Li which absorbs that. So these terms, these quadratic terms come with power 1 each term. Okay, and this will of course then change, and the constant will also change. And then you do then you complete the square. Okay, that is exactly the same step as we had done long back. Somewhere here. Here, how did we reach here? We reached here by completing a square. Here, this step. Okay, and then we had to shift the momentum. So after you have completed the square, okay, so this is a loop momentum, and that's what you get after completing the square. So you do this similar step, and then you shift the momentum. Okay, and that's what you should do here as well. So I leave it as an exercise for you to do. Okay, so exercise, complete the square. Okay, after you have gotten rid of these coefficients by redefining, and then you shift the momentum, shift the loop momenta. Okay, and it will give you the following. So that's an exercise you should check. Apart from some other factors which I am not writing, you will get the following: 0 to 1 dx1, 0 to 1 dx n number of propagators, delta of x1 plus x2 plus xn minus 1 times integral d L1 n. I hope I'm not changing the notation. Yes, correct. Then dl1 dn minus 1 L1 over 2 pi to the n. Did I write 2 pi to the n earlier? I forgot. So here I should have written 2 pi to the n. Okay, and for each loop momentum you have this dl L, because you have L loop momenta, L, okay, so over 2 pi to the n. Good, and then you should check that this is the result that you are going to get, times 1 over I have renamed the loop momenta again to L. Okay, L1, L2. So I'm writing the result because anyway L is dummy, so I'm writing it this way. Square minus capital M square, I epsilon has been dropped, power n. Okay, check this, that this is what you get, where m square is of course a function of m square is a function, so it's not writing now, the function of xi's, then it will be function of pi dot pj, and it will be a function of m square. Okay, these are the things which will enter m square. Okay, and now this is looking very good. I'll just write one more step. So this L1 square plus L2 square plus LL square, let me just write it in a more expanded form so that we are 100% sure that we understand what we are writing. This is the following. What is L1 square? L1 square is L1, the first component of it, squared, plus the second component of it squared, so and so forth, nth component of it squared. Right? Then what is L2 squared? Similarly, you change the subscript 1 by 2, and then finally you have LL, which is LL first component squared. Okay, we are in Euclidean space, that is why it's all pluses, there is no minus. LL n square. Okay, so now let's define a new vector which I will call LE, which is let me define it first, it will be easier, which is L, these are the components, L11, L12, L1n, then it has L21 up to L2n, okay, then L1, L, n. So that's the LE vector, okay, in the Euclidean space. That's a new vector. So what's in the denominator? This just becomes LE square. So the denominator is minus LE square, L Euclidean square, minus m square, also check that m square is positive, power n. Okay, that's your denominator. Let's look at the numerator. Numerator is what? It is just this. So it is DL11, DL12, DL13, so and so forth, DL1n, which is exactly this one. Okay, then you have DL21, DL22 and so forth up to DLLN. That will be what you have here, and this is the last one. Okay, so you see that what you have here in the this integral, the differentials, that is same as the following. DLn minus 1, here I wanted to write n, up to DLLn dn minus 1 LL. This is what? The way I have defined the new vector LE, this is DLE. But what is the total dimension of this differential? It has total L such, and each of them has n. So this is n L. And there are total n L differentials here. That is why I have written D N L L E. So the integral, the Feynman integral, apart from other factors, is this. It's not writing. Times 1 over minus, I will use a square bracket, minus L Euclidean square, okay, minus m square power n, okay, where m square is positive. Okay, good. So that's how an arbitrary Feynman integral is going to behave. There are other factors which I have omitted, but they do not carry the loop momenta. Now you can do the same thing. You can do the angular integrals and the radial integral. Angular integrals are not going to give you any divergences, and here anyway an angular integral just separates out easily, right? Because what you have here is only radial, it depends only on the radial part. There is no angular part in here, okay? Because just look at this 2 dimension, this is LE square. The square of the magnitude will be LE square, okay? And this does not depend on the theta, okay? Even if it is here, it's the same LE square. So the denominator doesn't depend on the angular variables. So the angular integral is trivial. You can, okay, we'll see the angular integral later, but at least it filters out and sits outside of the radial integral, and then you can do the radial integral. So this is same as angular part times the radial integral. Okay. So when does this diverge? Now the reason I have written it in this form is because earlier we had problems because of the Minkowski space. Now I don't have any such problems, so I can just count the degree of divergence. So when does this diverge? It diverges when NL minus 2n is greater than or equal to 0. Okay, if this condition is satisfied, then it is divergent. Okay, if NL minus 2n is less than 0, then it doesn't diverge. Okay, let me remind you again. Capital N is the number of propagators. Okay, and small n is the number of dimensions. So what does this say? Let's take n equal to 4 and L equal to 1. So let me write down this again. Okay, I will write down the expression also. So here integral dnl Le over 2 pi nl. Did I write that earlier? Yes. Then you have 1 over minus L Euclidean square minus capital M square power n. Okay, and as I wrote just now, if n L minus 2 times capital N is greater than equal to 0, greater than or equal to 0, then this is UV divergent. Okay, and remember, angular integrals cannot give any UV divergence. They have finite volume. Okay, so let's look at n equal to 4, meaning 4-dimensional space, which is our space, and L is equal to 1. So 1 propagator. So this condition says that you have something. Yeah. So this is n is 4, L is 1, minus 2n should be greater than equal to 0. Okay, which means that n should be less than equal to 2. Okay, and what was n? Capital N was the number of propagators. right? So it says that if you are looking at one loop in 4 dimensions, if you are looking at Feynman diagrams which are defined in 4 dimensions and it is at one loop, then that Feynman diagram is going to diverge if the number of propagators is less than 2 or equal to 2. You remember, if you increase the number of propagators, the integral starts behaving nicely in the ultraviolet anyway, right? Because each time you have a additional propagator, it brings an additional power of 1 over k square in the denominator. So this is saying that things are bad till you are having 1 or 2 propagators, which you have seen already, right? This is consistent with what we have learned earlier. So if you are looking at 4 dimensions and at one loop, L is 1, meaning one loop, and you have this is divergent. Okay, it has one propagator. This is the case for n equal to 1 propagator. Then we have also seen that at one loop, these diagrams diverge. Okay, and these have L equal to 2. Sorry, not n equal to 2. Okay, the number of propagators is 2, 1, 2. So you see all these diverge precisely for this reason. This is the counting which we have found. So this is what is giving the divergences. And if you go to this case where this is still one loop, so L equal to 1, n equal to 4, and look at this diagram, this did not diverge because it has 3 propagators and 3 is bigger than 2, and when n is bigger than 2, then this is not going to diverge. So you can see that the calculation that we have done is right. We have not made any mistakes because this matches what we already knew. So this is in phi to the 4 theory, whatever examples I have just now given. Okay, we can also look in phi cube theory and see whether it is all consistent. So in phi cube theory, let's again at L equal to 1, that is one loop, and let's look at D equal to 4 dimensions. This is 3-point vertex in phi cube theory. Okay, so that's how many propagators you have here which are involved in the loop integral. There is one. It's only one, this propagator, right? Not this one. This one is not involved in the loop integral. So this one, and this diverges because it's only one propagator, n is equal to 1. How about this? This is 3 propagators, one loop, 4 dimensions. So this will be finite, right? Ultraviolet finite, and which is true because it brings 6 powers in the denominator. You have 4 powers in the numerator. So this is also consistent with what we have found here. Okay, so we have now seen that the source of ultraviolet divergences and how to see them correctly by doing a Wick rotation. Now our next task will be to look at regularizations, different kinds of regularizations I will talk about in the next video. You have seen already one, the cutoff regularization. I will also talk about polyvillars and dimensional regularization. And then once we have done the regularization, meaning how to make integrals finite but dependent on the regulator, we will proceed to do the renormalization, okay? How to remove, how to subtract the infinities to get finite answers. Okay, so see you in the next video.